Welcome dear learners. We are continuing Unit 4, Fundamentals of Analytical Chemistry. In the present module, we are discussing indicators in volumetric analysis. This module is intended to discuss all type of indicators which are commonly used in volumetric analysis. So, the contents of this module are indicators, their definition, theory of acid-base indicators, redox indicators, adsorption indicators, complexometric indicators, and double burette method of titration. In addition to indicators, as the last part, there we are dealing with a procedure called double burette method of titration. These about the contents. First of all, indicators. Indicators are substances that change color at a specific pH or at the end point of a reaction. We have to make one point very clear. What is the difference between end point and equivalence point? Equivalence point is the theoretical point at which the reaction between analyte and the titrant is completed. However, it is not possible to exactly locate the equivalence point of a reaction. But an indication of equivalent point is possible to detect. That is called end point. So, theoretically, end point is different from equivalence point. But for practical sake and calculations, we are taking end point equivalent to the equivalent point. Indicators are substances used to find out end point of a reaction. That is, indicators will give a color change nearing to the end point. These indicators help in visually identifying the completion of a titration. There are several types of indicators and these involve acid-base indicators, redox indicators, adsorption indicators, complexometric indicators. So, these are very important category of indicators and the present module is intended to have a thorough discussion on these type of indicators. And now we can have a glimpse on different type of indicators. First of all, theory and elementary concepts associated with acid-base indicators. Acid-base indicators are substances showing color change according to the hydrogen ion concentration of the solution. It should be noted that the hydrogen ion concentration is quantitatively expressed in terms of pH. pH is negative logarithm of hydrogen ion concentration. If the hydrogen ion concentration is high, pH will be low and vice versa. So, acid-base indicators work or they will show color change according to the hydrogen ion concentration or simply the pH of the solution. The change from predominantly acid color to predominantly alkaline color takes place within a small interval of pH known as the color change interval of the indicator. Suppose you are having an acid-base indicator X which is having blue color in a particular acid medium and a red color in some other alkaline medium. This color change from blue to red occur within a very small pH range and that range is known as color change interval of that indicator X. Now, a suitable indicator for an acid-base titration is the one which shows a distinct color change at a pH very close to the end point of the titration. how much this pH is close to the end point, the more accurate will be the determination of the end point. Now, theory of acid-base indicators. The first useful theory of acid-base indicators was proposed by W. Oswald, based upon the concept that the indicators are very weak organic acids or organic bases. So, according to him, according to W. Oswald, the indicators are very weak organic acids or organic bases. The undissociated indicator molecule shows one color, while the ions furnished by it on dissociation shows another color in solution. That is, ionized form and unionized part has different colors. Consider a weak organic acid indicator. According to Ostwald, the indicator may be weak organic acid or weak organic base. Now, for the sake of the convenience, we consider the indicator as a weak organic acid. Let that weak organic acid is having the molecular formula SIN. H represents the hydrogen part and IN represents the indicator part. So, SIN is the weak organic acid indicator. The equilibrium between the undissociated acidic form HIN and the ionic form can be represented by using this expression. HIN reversibly gives H plus IN minus. The undissociated form has color A and IN minus, that is the ionized form or ionic form, has the color B. So, there occur the formation of two colors. Ionized form and unionized form has two different colors, namely A and B. The undissociated molecule HIN shows color A, while the ion IN minus shows color B. The equilibrium constant, this is a reversible reaction, then it is possible to represent an equilibrium constant, and that equilibrium constant is marked as KIN, which is equal to concentration of H plus into concentration of IN minus divided by concentration of HIN. From the expression for the equilibrium constant Kn, it is clear that H plus, concentration of H plus is appear in the numerator. Concentration of H plus is sometimes expressed as pH. So, this equilibrium constant Kn has a close connectivity with the pH of the solution or pH of the medium or H plus ion concentration. We can enter into more details of that. The color depends on H plus ion concentration because indicator constant Kin depends on concentration of H plus. Concentration of H plus is connected to pH. So, the equilibrium constant as well as the color depends on pH of the solution. The different indicators have different pH ranges of applications. So, the selection of a proper indicator is of paradigm importance, is of very much significance in acid-base titration. Some commonly used indicators, their pH range and color in acid as well as alkaline medium are shown here in the tabular form here. There are several acid-base indicators. Their pH range is also shown. Color in acid solution, color in alkaline solution are shown separately. The common indicators include cresol red, thymol blue, bromophenol blue, methyl orange, methyl red, bromothymol blue, phenol red, cresol red, thymol blue, phenolphthalein, thymolphthalein, etc. There are enormous acid-base indicators, and you are familiar with the two important type of acid-base indicators. They are nothing but methyl orange and phenolphthalein. They are also included in this chart, and this methyl orange has a pH range of 3.1 to 4.5, and this methyl orange is red in acidic solution and it appears to be yellow color in alkaline solution. So the color change is between red and yellow. Now the most important another indicator, that is phenolphthalein, is also appeared here. For phenolphthalein, the pH range is between 8.0 to 9.8. Remember, it is colorless in acid medium, but it is pink in basic medium. So the color change is from colorless to pink. So there are enormous acid base indicators. Each indicator differ by their pH range and their color in acid as well as basic medium or alkaline medium. Now we are taking two representative examples for a thorough discussion, since the two common acid base indicators, methyl orange and phenolphthalein, are popularly used in acid base titrations, out of which we are taking methyl orange first. Methyl orange shows color change from red in acid solution to yellow in basic solution. This picture represents the color change. We can have more details whenever we will demonstrate the laboratory experiments in the coming modules. Methyl orange can be used for titrations between SA and SB. SA stands for strong acid like HCl, H2SO4, etc. SB stands for strong base like NaOH, KOH. And this methyl orange is also used for titration between SA and WB. SA stands for strong acid like HCl. WB stands for weak base. So methyl orange is useful in titration between strong acid, strong base, and strong acid, weak base. Weak base include bases like NH4OH or ammonium hydroxide. So SA against SB, SA against WB are the two positions where we can use methyl orange as the indicator, and this selectivity is based on the pH range of methyl orange. Now moving on to another common indicator in acid base titration, it is nothing but phenolphthalein. Phenolphthalein is a colorless substance in acid solution and it turns to pink in acidic solution. The picture clearly reveals the color change from colorless to pink, and it should be noted that the phenolphthalein is useful in SASB titration, strong acid, strong base titration. At the same time, weak acid can also be titrated against a strong base by using phenolphthalein indicator. Weak acid include acetic acid, formic acid, etc. Now we are entering into other category of the indicator. They are nothing but redox indicators. A redox indicator or a redox indicator is a substance which shows different colors in oxidized and in reduced form. They are useful in redox titrations like dichrometry, iodometry, iodometry, etc. Let the indicator is marked as INOX, that is indicated in the oxidized form, plus N electron, you are getting ion in the reduced form. And according to Nernst equation, it is possible to set out an expression like this: E is equal to E0 indicator plus RT by NF into natural logarithm indicator OX divided by indicator in RED. Indicator in RED represents indicator in reduced form. Indicator in OX represents indicator in oxidized form. This is the Nernst equation corresponding to the equilibrium as shown here. So indicator can have, redox indicator can have oxidized form and reduced form. Their concentration can be related to the EMF of the system, EMF of the indicator by the relation. This relation is nothing but the Nernst equation. Now, for a sharp color change at the end point, the standard potential of the indicator, E0 indicator, should lie between the standard potentials of the oxidation reduction systems being titrated against each other. Now, during a redox titration, the analyte and the titrant undergo an electron transfer. The redox indicator changes color when the potential of the solution crosses a certain threshold in signaling that the titration endpoint is near. Now, common redox indicators are given in the tabular form here. The first column represents the indicators. color in oxidized form, color in reduced form, and approximate E0, standard EMF of the standard potential of the indicator is also shown in the last column. We can have a glimpse on various popular redox indicators. It includes methylene blue, which is blue in oxidized form, red in which is colorless in reduced form, and its potential is positive 0.01 volt. Similarly, diphenylamine having violet color in oxidized form, which is colorless in reduced form, and its potential is plus 0.76. Third redox indicator is ferroin, which is red in oxidized form, blue in reduced form, and the EMF is, the potential is plus 1.06. Finally, N-phenyl anthranoic acid, NBAA, which is red in oxidized form and colorless in reduced form, is associated with the standard potential of 0.85 volt. Now, external and internal indicators. In titrations involving dichromate, that is in dichromate titrations, since the potassium dichromate K2Cr2O7 is not a self-indicator like KMnO4, both external as well as internal indicators can be used to detect the endpoint. Potassium ferricyanide, abbreviated as K3FeC in 6 times, is used as an external indicator in dichrometry. This is a nice example for an external indicator. It is used for titrations involving Fe2 plus with K2Cr2O7. This point we made clear when we studied about dichrometry. Fe2 plus reacts with the ferricyanide ion to form Turnbull's blue, which is having a deep blue color, which is a deep blue complex. Small drops of ferricyanide solution are placed on a white tile during the course of the titration. During the titration, small drops from the reaction mixture are removed using a glass rod and spotted onto the indicator drops. As long as Fe2 plus is present, a blue color persists or appears. At the end point, when the end point is reached, no blue color forms on the spotting, which indicates that all the Fe2 plus ions or complete oxidation of Fe2 plus ions to Fe3 plus ions. Now in dichrometry, there is other category of indicator that I already mentioned. It is nothing but internal indicators. N-phenyl anthranoic acid, abbreviated as NPAA, and diphenylamine are two popular internal indicators. This is about the structure of the N-phenyl anthranoic acid and diphenylamine. This is about the chemical structure. And these indicators, NPAA, that is N-phenyl anthranoic acid and diphenylamine, are useful for titrations involving Fe2 plus ions with the potassium dichromate, with the acidified potassium dichromate. Now we can enter into more details of these internal indicators. First of all, N-phenyl anthranoic acid, which is nothing but NPAA. In the reduced form, N-phenyl anthranoic acid is greenish or colorless, and in the oxidized form, it turns to a violet red or purple colored material. During the titration, Fe2 plus is oxidized to Fe3 plus by potassium dichromate in acidic medium, and as long as Fe2 plus is present, NPAA remains in its reduced form or colorless or pale greenish color form, and once all Fe2 plus ions are consumed, excess of dichromate now oxidize N-phenyl anthranoic acid, and the oxidized form has a different color. The indicator is oxidized and produces a sharp color change, which is from green to violet red. This is because violet red is the color of oxidized form of N-phenyl anthranoic acid. Now the second indicator, that is nothing but diphenylamine. Diphenylamine is colorless in reduced form and turns intensely blue-violet in oxidized form. During titration with acidified potassium dichromate, Fe2 plus is oxidized to Fe3 plus. The indicator is only oxidized after all Fe2 plus is consumed. At the end point, K2Cr2O7 oxidizes the indicator, giving a sudden blue-violet color. When diphenylamine is used as indicator, some amount of syrupy phosphoric acid is added. This is to mask Fe3 plus ion, which would otherwise prematurely oxidize the indicator. That is, without phosphoric acid, you will get premature equivalent point or end. We are discussing adsorption indicators. Adsorption indicators are special dyes used in precipitation titrations, particularly for halide ions like Cl minus, Br minus, where the end point is detected by a color change due to adsorption onto the precipitate. That is, at the end point there occur the selective adsorption of the indicator on the surface of the precipitate obtained. Now, the working of adsorption indicator are shown here. During the titration, for example, Cl minus with AgNO3, silver ions react with the chloride ion to form AgCl precipitate. Before the equivalent point, the precipitate surface is negatively charged due to the presence of the Cl minus ion which is present in the medium. At the equivalent point, Cl minus ions, all the Cl minus ions are consumed, and slight excess of Ag plus may present in the solution, and the surface of the AgCl precipitate will become positively charged due to the presence of this excess Ag plus ions. The anionic dye, that is the adsorption indicator, then adsorbs onto the positively charged surface and undergoes a visible color change. This is a chart showing popular adsorption indicators. The first column represents the indicator. Color before the endpoint and the color after the endpoint are shown here, and typically useful for the estimation of some ions. The ions which can be estimated by that indicator is also shown in the last column. The indicators include fluorescein, eosin, dichlorofluorescein, and for fluorescein, before the endpoint the color change is yellowish green, and at the endpoint or after the immediately after the endpoint the color change is pink, which is used for estimation of the Cl minus ion. Eosin is yellowish in the reaction before the endpoint, but after the endpoint it will be pink in color, used for the estimation of the Br minus ion. And finally, dichlorofluorescein, which is pale yellow before the endpoint, and after the endpoint it is pink red in color, which is useful for the estimation of Cl minus as well as Br minus ions. So, this is a list of popular adsorption indicators. Now, the last part of the present discussion, that is nothing but the complexometric indicators. The reaction involving complex ions or undissociated neutral molecules falls under the category of complexometric titration. This point is clear to you. Now, the indicators used in complexometric titration are called complexometric indicators. Complexometric indicators have a synonym. It is also known as metallochromic indicators. And these are organic dyes used in complexometric titration to detect the presence of the metal ions through a visible color change. Now, these complexometric indicators are organic ligands that form colored complex with metal ions. When a complexing agent like ethylene diamine tetracetic acid is added, it displaces the indicator from the metal ion complex due to strong binding, causing a distinct color change that signals the endpoint. This is the working principle of complexometric indicator. The metal ion, preferably calcium 2 plus or magnesium 2 plus, initially forms a weak complex with the concerned indicator. This is a colored species. During the titration, EDTA, which is a strong chelating agent, is added to the reaction mixture, and EDTA binds more strongly to the metal ion and displaces the indicator. The indicator is now free in solution, returns to its original color, signaling the endpoint. Now, popular complexometric indicators. This is a list of popular complexometric indicators. There are enormous indicators, out of which I have selected 2 important indicators only. And these indicators are areochrome black tea and muroxide. Areochrome black tea is wine red in color in its metal ion complex form, and it is blue in color when it is free, or the free indicator is having blue color, which is highly useful for the estimation of ions like magnesium, calcium 2 plus, zinc 2 plus. And the next indicator is muroxide. This muroxide indicator is pink violet in the indicator complex form, and it is yellow in free form. So, the color changes from pink violet to yellow. It is highly useful in the estimation of calcium 2 plus ions. This about the popular complexometric indicators. This about the last part, and this part is not associated with indicators. This is a special kind of titration that we adopted during volumetric analysis. This procedure is called the double burette method of titration. We can now have details on this new method. This is nothing but double burette method of titration. In the titration method, in the common titration method we adopted, we are using on burette and on pipette. But the double burette method of titration is the titration method, or it is the titration method using 2 burettes without using pipette. The principle and procedure of the double burette method can be illustrated by taking the titration of sodium hydroxide against HCl. This we can illustratively studied by taking 2 things, NaOH as well as HCl. Now, you can take 2 burettes, and burette 1 is set with HCl and burette 2 is set with NaOH. 16 ml of NaOH is added to a conical flask from burette 2, because burette 2 is filled with NaOH, and you have to pour an aliquot of 16 ml of NaOH from burette 2 into a conical flask. 1 drop of indicator, that is phenolphthalein or methyl orange, both can be used. Since you are dealing with the titration of NaOH against HCl, that is a strong acid against a strong base, you can use these 2 type of indicators. So, you can put on drop of indicator like phenolphthalein or methyl orange. It is added in 1 drop. It is then titrated with HCl, which is taken in burette 1, and the end point is determined. So, you got an end point corresponds to 16 ml of NaOH. Now, from this titer value, you can calculate the normality of unknown concentration using the relation VNaOH and NaOH is equal to VHCl into NHCl. This is theoretically equal to the important volumetric relation V1N1 equal to V2N2. This is modified for the present titration. Now, to this solution left in the conical flask, you can again add 2 more ml of sodium hydroxide from burette 2. It is then titrated with HCl from burette 1. You will get a new endpoint. Again also you can calculate the concentration by using the similar expression, and you will get a new normality value, and you have to repeat the process by adding 20 ml, 22 ml and 24 ml of NaOH, and normality is calculated in each step of the reaction. Average of all these values is taken as the normality of the unknown solution. It is also possible to find out the final value of the normality using a graphical method. For this, you can plot. Alternatively, a graphical method can also be adopted to determine the unknown concentration. For this, the volume of HCl against volume of NaOH at each endpoint is plotted. You will get a straight line, and the titer value corresponds to any definite volume of NaOH. Say the volume of HCl corresponds to 19 ml NaOH, 21 ml NaOH, 20.5 ml NaOH. Any titer value corresponds to fixed value of NaOH can be calculated from the graph. And these values can be used to calculate the normality. So, double burette method utilizes 2 burettes and no pipettes, and this double burette method of titration has several advantages, and we can have the advantages here. First one, pipetting can be avoided. Minimum chemicals are required as compared to conventional method because we are not repeating the titration. So, chemical consumption is minimum as far as the double burette method of titration is concerned. This procedure is highly time saving, or it is a time saving procedure. One drop of indicator is sufficient for complete titration. Now, more accurate result is obtained during the titration. That's all about the present module. Have a nice learning experience. Thank you.